Okay, good morning, everyone. Welcome back. Our first talk for today is by Alok Laddha from the Chennai Mathematical Institute, and he'll tell us, he'll talk about gentle blossom quivers. His title is From Gentle Blossom Quivers to the S Matrix. Over to you.
You can hear, right? Okay, thanks a lot to, first of all, to Pranav, Arvind, and Manjunath. I hope they don't regret it after this hour. So, yeah, I'm going to tell you something about a physicist view on some of the things that many of you find interesting, which is to make a connection from what a specific type of quivers, which are called dissection quivers. So I will explain all these words in the talk, and how they sort of, if you just follow a specific program in mathematics, they lead us to an extremely interesting class of data for physics, which are called S matrices. And one interesting thing about this program is that up to this point, there is no physics information at all. So everything up to here is done by mathematicians, and then all we have to do is realize that what they discovered are directly relevant to physics. So I will, so sort of Pinaki, if you were here last week, he went in opposite direction a little bit. So I will kind of go in this direction. I think many of you will know this much more than me. So please don't give me hard time if I say something not very rigorous, but hopefully the main ideas will become clear. Okay, so let me just start with, I think some of this construction you would have, and if I'm writing small also, please ask me to write bigger. So let me just start with a basic idea of why, what these dissection quivers are. So I'm going to start with a very simple example. So let's take just a, planar polygon and no puncture or anything inside, just a usual regular polygon. Now the idea is that let us consider any dissection of this polygon. So let me give one, we will look at two examples. So we are going to look at two dissections. One is a dissection into two triangles, it's example one, and the other one is just a dissection into one triangle and one quadrilateral. And what, as we will see that both of these dissections give you a class of combinatorial polytopes. So I haven't defined a quiver yet, I will come to that in a minute, but both of these dissections naturally give us a class of polytopes which fall under a class called accordiahedra. And I think most of you are familiar with what kind of polytope we get from here, which are called associahedra. So this one gives us a two-dimensional associahedron. And this one is maybe not that familiar because it was discovered only recently, maybe a few years back. And this one gives us what is called a one-dimensional polytope, one-dimensional accordiahedron. Yeah, exactly. Yeah, so I will explain the construction now, and then we will see that why they are directly tied to a concept of some quivers that we will. So just to give you an example, that this given a dissection, this give you a trivial quiver because you just put on these internal edges two vertex like this. And now if you give me some orientation inside each cell, so just to indicate the external edges, distinguished from these ones, I'm going to draw hollow vertices on them. And now let me give you just some orientation inside this, that in every one, I'm going to draw arrows which are clockwise. So I go this way. Then I go this way here. And similarly here, this way. And so then this, this specific, this is an example of a quiver with two vertices and a relation between them. Here, of course, the quiver is trivial because if I follow the same procedure, then I just have a vertex like nothing else, right? So these, when I talk about a dissection quiver, all I mean are the quiver generated by dissections. So these are two examples of a quiver. So now let me explain to you how these dissections generate combinatorial polytopes. So I'm going to use a slightly unorthodox definition for associahedron, which may look unnatural, but the advantage is that all these accordiahedra fit into that single definition. So let me just do that. So let's just start with this example first. So we just start with and now what I'm going to do is draw a dual polygon to this one. So let me just draw Now let us look at, so all we have to do is look at consider all chords in the dual pentagon, which follow a simple rule that if I consider a chord, whenever it enters a cell from one side, it can only exit a cell from a side which is adjacent to that side. So for example, if you start from here, it can only, of course, here it's trivial. If you start from here, this, you can draw a chord which is this one, but you can also, of course, draw the other one. So both of these are allowed chords. And now you see that this configuration gives you a triangulation of the dual pentagon. And if I just label these vertices as, so let me just label them as just tilde to distinguish it from that they are part of the dual. So you see that one allowed triangulation of the dual is, but of course you could have immediately convinced yourself that instead of 1, 4, if I consider 1, 4 tilde, if I consider 3 tilde, 5 tilde, that's also allowed chord because you are entering this cell from this side and exiting from an adjacent side. So you're okay. So then.
Can you just repeat what is the rule for when it is allowed?
So here the rule, which is a bit trivial here, you will see why the rule is not trivial, is that if a chord enters a cell, then it can only exit the cell from a side which is adjacent to the so if okay, when you come here, it will become clear what I mean maybe. So right now the only rule is that if you are entering from here and you are exiting from here, and these two are touching at a vertex. So it's an allowed chord. So if you follow this route, then you will trivially get associahedron because all the chords are allowed, and each such pair will give you a triangulation. And you can, so, and of course, as you know, the rule of the associahedron is that these two are adjacent if they have one common chord between them. And the one common chord between these is 1, 3 tilde. So we can just follow this route and we get a combinatorial polytope.
Can you please explain again, like when we say that a chord is allowed?
Yeah. Actually, I should have done this example first. Just give me 1 minute. When I do this, you will see when it's not allowed.
Oh, sure.
That will maybe that will be helpful. So usually we don't do this for. I mean, the way we define associahedron is just look at all triangulations, and you say that two triangulations are adjacent in a in the polytope if they share one chord common, and so you are only allowed to do one, like you are doing one flip here in this case, but I'm doing a slightly, it looks like I'm doing a definition which is slightly redundant for the associahedron, but you'll see that definition will give us a polytope here. So yeah, so here I'm just writing all chords are allowed, and so then we get a combinatorial polytope, which is a two-dimensional associahedron, which is the A2. But let me do this rule where it will become clear what is not allowed. So let's do the and so again I draw the dual. So now you see that if I look at the 1 tilde, 3 tilde, then that is allowed because of course you are entering here, you are exiting here, and you are entering here. But if I ask, okay, is 1, 4 allowed? Then you immediately see it is not allowed, because if I look at 1, 4, it is incident here, it enters here, but it exits the cell here, and these two are not adjacent. So is that, so the one allowed. UFN is allowed, 1, 3 tilde is allowed, but so 1, 4 tilde is not allowed.
So again, why is 1, 4 tilde not allowed?
So say that again.
Why is it not allowed?
So that's the rule we are putting. So we are going to look at all the dissections of the dual, which are allowed, and by allowed we mean we are putting this rule that a chord is allowed if it enters and exits any cell on incident edges. Incident means they should meet in a vertex. So this chord is entering this chord 1, 4. If I draw it's and if I look at this cell, it's entering it in 1, 3, but exiting in 4, 5, which are not incident edges. So 1, 4 is not allowed. And if you follow this, then you will see that only one more is allowed, and that is 2, 5, 2 tilde, 5 tilde, because it enters here. So, it's entering and exiting on an adjacent edge and then exiting here. So you can immediately check that only 2 chords are allowed. And so you get a one-dimensional combinatorial polytope, which is called a one-dimensional accordiahedron. I'll write it as AC. But notice that this, unlike the Associahedra, where here I chose 1, 3, 1, 4 as a reference kind of triangulation. But of course, I could have chosen any triangulation. I would have generated all the vertices of the. So the combinatorial polytope would not change. It's not sensitive to this wide triangulation. But here clearly you can convince yourself that it's sensitive to the reference that I started with. So that I get a one-dimensional Associahedra, but I have to put. I'll put 1 here just to indicate dimension, and I put 1, 3 here to see the reference that you have started with. So I'll now give you one more example, which I won't work out, but just if you work out, you'll see that it makes sense. So suppose I consider yes. So right now we just combinatorial. So I should just think of it as a relation that there are 2 vertices and they are adjacent if you can go from one to the other by 1 flip. Yeah. Yeah, it will always be one-dimensional with different labeling of the vertices. Yes, you are right. So if you yeah, exactly. So I just give you one more. I just write down one example, which is slightly more tedious, but really interesting to work out. Is that suppose now I start with dissection, which is this one. So it is breaking my hedragon into 3 quadrilaterals. And now if I follow this route, then you can immediately check that the combinatorial polytope you get is, so the dimension of the polytope always is same as the number of dissections that you start with. And then the polytope you get is a square, and the labeling is the following. Oh, sorry, 1, 4 tilde, 5, 8 tilde. See, this is the one I'm starting with. So whatever you start with, the dual is always allowed. Like you can just convene yourself, but then you will also have one. Then there is and I think this is what you will get. So this is an example of accordiahedron where the reference is 1, 4 and 5, 8. And this actually was discovered in a different way first by Barashnikov, and this was called Stokes polytope. It goes by another name. That is, if you start with reference, which is breaking your n-gon only into quadrilaterals, then the accordiahedra was discovered by some independent mathematician. It was called Stokes polytope. But now we know that there's an entire family of these polytopes, which you just start with a dissection, reference dissection, and you generate this family of combinatorial polytopes. So, and the dissection quiver, so far what we have realized are very trivial. So I mean, in this case also, we can just, I will just write the quiver just for illustration. So when I write the dissection quiver, just one rule you should keep in mind is that if your internal chord is not touching an edge, then don't put this reference hollow vertex on the external edge. So because on 2, 3, this dissection or this dissection is not incident on 2, 3. So when you draw the dissection quiver, don't put any hollow vertex here. So let me just draw, then it will become clear. So and I just follow orientation, which is clockwise. And so this part is the this part, which is a disconnected 2 vertex, is a dissection quiver. Like there is no connection between them. The reason there's no connection between them is because you cannot enter an edge here and exit here, because these 2 are not adjacent to each other. No. So yeah. So okay. So these are.
Alok, before you go ahead, just to make sure I understood correctly.
Yeah.
So I think I understood what the allowed what edges are. And then can you just repeat how do you get the polytope from there?
Yeah. So here we just start with So suppose we start with 1, 4, 5, 8. Now I want to look at all possible quadrangulations of the dual, which are allowed by the rule we set out. So if I start with, you can immediately see that if I draw 1 tilde, 4 tilde, then the only other allowed chord would be either 5 tilde, 8 tilde, or 4 tilde, 7 tilde by the rules we have laid out. Now if I now mutate, for example, if I have 4 tilde, 7 tilde, where the reference is still fixed, is this white one is still fixed, then the only allowed chord will be either 1 tilde, 4 tilde, or 3 tilde, 8 tilde. So I just follow that rule and I say that I only have 4 choices, and that's it. Okay, so these are the class of combinatorial polytopes. So as you can see that it is, you just, for any reference, you will get a polytope like this, closed polytope like this. So this is of course a theorem. I mean, it's not above my pay grade to prove it, but it's something that was proved, I think, in, I will give the reference in the end in 2017 by, I think they were the first one to prove this. Yeah. No, so you can pick any, right? Like the point is you start with any reference dissection, you'll always get a combinatorial closed polytope like this if you follow this rule. So sorry, dissection is just this. By dissection, I only mean this process that you dissect the 8-gon into 3 quadrilaterals. So these are my dissections. Exactly. Yeah, sorry, I would, I should say it more maybe carefully. But and when I say reference dissection, I only mean the white ones. Okay, so that gives us this combinatorial polytopes. And now it turns out that there are the specific realizations. That is, we can draw these polytopes. We can give them shapes, as Naveen was asking, in Cartesian space by simply following some either quiver representation theory that we saw in the talk yesterday, or a realization that given these quivers, we can lay out some rules and write down some linear equations which will chart out these polytopes in the Cartesian space. So that is what I will. So that is this part of the title. That so far I haven't told you what these blossom things are or these gentle things are, but now I will tell you how there is a specific way that we can draw them just from some mathematics results into Cartesian space, and that will lead us to this specific realization. I think someone asked yesterday in Maitri's talk what is realization. So I think as she explained, realization is just drawing them in a space, in a Cartesian space. Okay.
A quick question.
Yeah.
So there you've written quiver goes to polytope, but in the way it's constructed here.
Yeah. Sorry, I mean my arrow should be taken schematically. It is more of a, when I said quiver, I could have dissection. Quiver means I start with a reference dissection, but given a reference dissection, I have a quiver. Right. So that's all I meant. So I could have just written here reference dissection.
So the dissection gives rise to both the quiver and the polytope. Sort of.
Exactly. So given a reference, and these rules tell us how to get these polytopes. And now I'm going to say that the same, we have to enhance this quiver a little bit, and it's going to give us some rules which are going to give us these convex realizations.
Right. And your quiver will be without loops always?
Sorry?
Your quiver will never have loops, right?
No, it will have. It will not have a 2 cycle, but it can have, of course, you're right. It will have. It can certainly have closed cycles. I don't know if that's what. So if you start with reference, which is, let's start with this one. So then you have closed. I mean, you have a quiver which is closed, but not a 2 cycle. I think you'll never get in this case. You'll never get this. Right. This you will not get, but you will get. They are not acyclic. I think acyclic. They are not acyclic always. You get a cyclic quiver.
Yeah. What tells us that we should? What tells us that we should choose this clockwise orientation on all the segments that you draw?
Yeah. So the point is that, as you will see, that once you choose this clockwise orientation, and you are going to be able to discover specific realizations of these polytopes. And for associahedra, this realization match with what people obtained through quiver representation theory.
Because typically in quivers, we choose an orientation so that we don't allow these cycles to exist, right?
That's true. So yes, I mean, if you look at, for example, the quiver representation theory way of getting a realization of the associahedron that was explained in the yesterday's talk also, you could not start with this quiver. Yeah, but now the improvement over that work, which was done in 2019, which are the rules I am now describing, told you that you could start even with cyclic quivers and you get realizations. And the places where quiver representation theory coming from cluster algebra work, these realizations match.
I see. And sorry, just have one small
Yeah.
question. So given a dissection, you said you get a quiver, but is the opposite arrow also true? Like,
No, I don't think. No, I don't think all quivers give you dissection. So these are specifically called. But this I think mathematicians don't know more. So these are specifically called dissection quivers. The quivers which are associated to dissection of a polygon. In fact, I don't know if I will have time, but so far I'm looking at unpunctured polygons. But you will see that there are dissection quivers even if you put punctures inside them, and they all carry information about S matrix of some quantum field theory. So
Thanks.
So quiver, in other words, is a directed acyclic graph, right? For combinatorial.
is it always acyclic? I know it can have cyclic. I mean, isn't this
Directed cycles? It can have directed cycles.
Yeah, wouldn't that be a I mean, so let me just let me ask, isn't this if I just look at this one, it's not a acyclic quiver, but isn't still not a quiver, so let me draw it. So it's yeah, exactly. So this one is a quiver, right? Isn't it's okay, right? I mean, it's this one. So let me draw it separately. So this is the 1,5 vertex. This is the 1,3 chord, and this is the 3,5 chord, and the orientation. This is our.
Oh, so you allow such cycles?
Yeah, we allow cycles. So the point is that now, I think that when you do these realizations of associahedra from cluster algebra, your seed has to be acyclic. I think that's the work that Thomas and yesterday the work that was referenced also in Maitri's talk. But the new way of looking at it through this blossom quiver is that you could even start with a seed which is cyclic, and you still get the realization. No, this is the quiver coming from the dissection. Right, so that's the quiver that is what I would call a dissection quiver. Now, no, we will not omit. So I will. So right now, so this is the this is what is called the dissection quiver from what I understand. And if you include these ones, I think it's like including these frozen variables in cluster algebra. Then it's called the blossom quiver. So, but we need the full one to do the realization, as we will see. Okay, so now I will just the time. Okay, I have time. Okay. So I will tell you what the convex realization are. So I will focus on these two examples just for concreteness, and then we can. So I'll give you the rules that mathematicians gave us. So this came through a paper of. In 2019, and what is interesting, which if I have time I will tell you a little bit, is that the investigation of this one was motivated from the paper that was referenced yesterday by Maitri, which was by Thomas and Beiser et al, which gave us what she called ABHY associahedra, ABHY realizations. And these realizations were actually discovered by some simple physics argument, which in the end maybe I will tell you by Arkani Hamad, by Hay and Yoon. So actually the chronology was opposite. Like ABHY discovered some specific realizations of associahedra in Cartesian space, which gives them some information about S matrix of quantum field theory. Then these mathematicians realized that actually these realizations come from quiver representation theory, and this work was extended by these guys so that you could do this for not only a quiver coming from triangulations but from any dissection. So for any accordiahedra you would get a convex realization, and interesting is all of them give you have data about S matrix of one or the other quantum field theory. So that's okay. So I will just give you through example explain the new way of doing this realization. So let me look at this example again. So I start with a reference. So now this, as you will see that even though the combinatorial associahedron is not sensitive to the reference, the realizations will be sensitive to reference. So given start with this reference dissection 1314, we get one realization. If you change the reference, you get other realization. And so it will become clear when I do this example. So now we have to draw the full quiver as Manjunath was asking. So let me just draw the whole thing. And we put this is the rule is that we put clockwise orientation in each cell. It's this way, right? Yeah. Okay, so I hope this is visible. So I hope it's not too small. And now I'm just going to give you a rule, and I think if there's time, we can. I'm giving you the final result that you have. So what we want to do is to realize this two-dimensional polytope in a space which is spanned by. So I'm giving you a final result. So please ask me if something is not clear. So let's say that we have a 5-dimensional Cartesian space, where this 5-dimensional space is spanned by variables which are labeled by, so the x's I'm just going to label them as all possible chords of the 5-gon. So I have some space like this, and what I want to do is draw my 2-dimensional polytope in this 5-dimensional space. And the rule is now the following. So that means I need 3 equations to draw the to draw this 2-dimensional associahedron. And the rule that these guys gave us is the following, and it's very simple to describe. So let us start with. So now we have to look at. So this full quiver, by the way, this full quiver is what is called the blossom quiver. And I think that I will just say something, even though if you ask me to argue too much, I won't be able to give you like some detailed explanation. Is that so? Given this, so this quiver is typically denoted as some, with some flower. So these hollow vertices are like frozen. So they are like they are blossoms. So they just stay there. And now the point is that starting from here, you can generate what is called a gentle algebra. So I'm just indicating it because most of you may be more interested in this. So starting with, so we have this Q hash quiver and the quiver Q, which is the dissection quiver we started with. And starting with Q, we can define a gentle algebra, which is all the paths which are coming. Maybe I should put notation this here, which are all the paths coming from all the paths which are in this generated by the path algebra generated by this divided by a specific ideal. And I'll just intuitively explain what this ideal is. Look at all paths of length at least 2 which belong to the same cell. So if you like this path, then in the algebra this should be trivial. You should not count this as a separate path. And so I think there is of course detailed theorem that this gives you a nice algebra, and this is what is called a gentle algebra.
So here you use the entire quiver, the thing including the frozen vertices.
Yeah. You use the entire thing. I think even though the notation, I may be a bit sketchy with the notation, but I'm pretty sure that when you actually, yeah, this I'm not entirely, although we will not use it. Yeah, sorry, I take that back. I apologize. You are right that it is just all the path or the path algebra generated by the. So it's really just this. So path algebra just generated by 3 elements right here, and then but I don't know then how. In this case, maybe this.
So in the previous case where you had that cycle, the triangle, there you'd have something interesting.
Yeah, so there we will have to quotient out. In this case, I'm not entirely sure. Maybe let me just leave it for a second. Maybe I come back to this later. We won't use it. We will use this full blossom quiver here that we have drawn. Okay. So now let me tell you the rules that we described. So now the point is the following: that we need 3 equations. And how do we get 3 equations? You have to look at all the elements of the quiver, not the blossom quiver. So there are 3 elements. So there is this one, which are vertices of the quiver, and and one path of length 1. So now for each of these, we are going to write one linear equation. That is the result of this analysis. And so let's look at this vertex. Now the equation is the following, that you look at, so let me draw the, again denote the dual with the tilde here. And now the point is the following, that now you look at a walk which is starting from, look at all possible paths which begin and end in the external edges. But now consider a walk which is where both the arrows are outgoing at this vertex. So there is only one walk of that type, which is 1 tilde, 3 tilde. And we say that that is a walk which hits a peak here. It is a walk of this type. So this is 1 tilde, 3 tilde.
So what is a walk? A zigzag path?
Walk is any string of paths in the full quiver where you begin and end on the external, on the tilde vertices only.
But you're allowed to go backwards along an arrow. So if an arrow is...
Yeah, you in
can go in the
principle,
opposite
but
direction.
you will never be able to in this case. Like
I thought you did here, no? You go from one to that yellow guy in the middle.
Yeah. You go here, and then
That's
you are
backward.
hitting here.
No? Isn't that the arrow is pointing up?
Oh, you are talking about arrow. Sorry. So when you are going here, the arrows are not, the arrows are telling you that there is a peak here. But the path you are describing is 1 tilde to this vertex to this vertex.
Okay, so
that's the path I'm looking at.
The direction of the arrow is not relevant.
The direction of the arrow is just extra data, which is telling you that there's a peak here. That's an additional data. It's data not captured in this. Yeah. So you are not composing based on the, you're not doing that. You can always, sorry. So when you define this algebra of paths, the composition rule always is that whenever a edge terminate, the usual thing. So there the arrows do not matter in the composition. So arrow is extra data. And now there is only one path, as you can see, which is a dip here, where both the arrows are incoming. And the dip is something where, so here the peak is trivial because the path ends here, 1 tilde, 3 tilde. But if you look at the place where both the arrows are incoming, then there are two possibilities. You can have, so the arrows are incoming. So this is a 2 tilde, this is 4 tilde. But now you see that at 4 tilde, you have two possibilities. You can go 5 tilde or you can go to 4 tilde. But now,
I don't see a path.
you can go to 4 tilde or 5. Okay, this is 3 tilde, 5 tilde, sorry. And now from here, there are two possibilities. You can go to 5 tilde or you can go to 3 tilde, 2 tilde, 4 tilde.
From 2 tilde, you went to...
For 2 tilde, we want to first look at the path where both the arrows are incoming. That's called a dip. So that is, you are here. But once you reach here, you can go either here or here. So far, I haven't told you which one to choose when you have a dip.
I guess I didn't understand the notation. So you go from 2 to, what is that arrow on the peak?
So this 2 tilde, you are incoming.
Yeah.
This is your vertex. So let me call this 1 tilde, 3 tilde vertex.
Okay, so that's the one.
And this one is also incoming. And this one is this vertex, which is what I call 3 tilde, 5 tilde vertex. And now I have two possibilities. I can go towards 4 tilde or 5 tilde.
So in this case, you're able to label these internal vertices by pairs of...
I'm just labeling it by the chord of the, exactly. So this yellow one I'm indicating with a pair. So, sorry. Yeah, you're right. Maybe I should call it like this. Thanks. Thank you. It's 1, 3 and 3, 5. I think that will be you'll be okay with that, right?
But in general, if I...
1, 4.
If I have a very complicated polygon, will you still be able to label the vertices by...
So this is just a rule I'm giving you now, that I look at this path, take this vertex, I look at a path where both the arrows are incoming, and I want to look at the path starts here, it can end here or here, because it cannot end here because I'm not allowing path to traverse in the same cell. So I have to always enter a cell and exit the cell. And so now I have two possibilities. Now the allowed path, which is supposed to have a dip here, is something where if the two arrows are incoming here, all the subsequent arrows should be outgoing. So that means that so let me just write it. So these are called proper walks. And I'm just going to write them. So there are two proper walks. So this proper walk is something which begin and end on final tilde vertices, and they have a peak or a dip on the reference on the point that you are starting with. So a proper walk, which is proper walk at 1 tilde 1 3 vertex. there is the following one, which is 1 tilde 1 3 3 tilde. This is a proper walk which hits a peak, and 2 tilde 2 tilde 1 3 1 4 and 4 tilde, which hits a dip. So only 4 tilde is allowed, because if these two are incoming, then all the subsequent arrows have to be outgoing. Okay, that's what ruled out this path for me. Okay, so now I'm just going to write the constraint. So now we have this data. Now I'm going to write the equation. The equation is the following. Yeah.
And when do we have a peak?
So peak is when both are outgoing. The peak at 1 3 is if both are outgoing at 1 3, but everywhere away it should be all incoming then. So here it's trivial. So both are outgoing, right? This is outgoing, this is outgoing. So it's a peak.
Okay.
Peak at 1 3.
Okay.
So I have three data points: 1 3, 3 5, 1 4, and the arrow from 1 3 to 1 4. So this is a path of length 0, path of length 0, path of length 1. I'm going to write linear equations associated to all three. That's going to give me 3 equations. I'm giving you rules to write this equation, and that will give me the realization of the polytope.
Okay.
So now for the 1 3, the rule is the following: that so we have a path which has a peak. So it's starting at 1 tilde and ending at 3 tilde. So I'm going to write the equation which is x 1 tilde 3 tilde plus the path which has a dip. And there's a unique path. What is important is that, I mean, this of course has been proved by them, that there are always, given any part of the quiver length, path of length 0 or 1, there is always a unique path which is a peak or a dip at that at either 1 3 1 4 or this arrow. So that's the point. So this is a unique path which has a peak at 1 3. Then there is a unique path which has a dip. So I write this equation, and then minus, all I have to do. So I can give more rule, but now in this case the rule is simple. Just subtract from it a variable which is and a variable which is this one, and put this as a positive constant. Now x2 tilde 3 tilde is 0, because there is no, that's the x variable associated with the external h, which is always we are setting them to 0. We are only assigning the variables to the possible chords in our game. So this thing is 0. So this is one equation that I got. Okay, similarly, I can write 2 other equations. So I mean, we can just write them. Finish this example. So in this case, you see that if I start with if I look at this as the vertex, then the path which has a peak is 4 tilde 2 tilde. So x2 tilde 4 tilde plus path which has a dip is 3 tilde 5 tilde minus again x2 tilde 5 tilde minus x3 tilde 4 tilde. And you put this as an arbitrary positive constant, any positive constant. So I'm just indicating it with the entry only indicates that what I started with, the position of this vertex, but that's not, it's just a label. And similarly, you can write the third one. And now the statement is that for any choice of these C's, any choice of C13, C24, and the third one, let me call it C13224, which are positive, there is a convex realization of associahedra in the embedding space. Okay, so that's the result. And so let me draw this now. Let me draw this realization in this case. So the realization looks like this. So although we are drawing it in R5, you can see that the associator actually is drawn only in the 1 3 1 4 plane, whichever reference that you started with. So it turns out that if you just look at this plane, then and you solve these equations, the associahedron you get is the following. So I will label the boundaries now, where this 1 tilde 3 tilde, where this face is x1 tilde 4 tilde equal to 0. This is x1 tilde 3 tilde equal to 0. This one is x2 tilde 5 tilde equal to 0. This one is x3 tilde 5 tilde equal to 0, and this one I think is x2 tilde 4 tilde equal to 0. And if you actually solve, you can see that this is a 45-degree line. And what is interesting about this realization as compared to many other older realizations, for example, one was discovered by Loday many years ago, is that you can see that exactly two pairs of faces are parallel to each other. And it turns out that this property is true in any dimension. So when you do this, when you follow this algorithm and you realize the associahedron, if the associahedron is d-dimensional, exactly d pairs of codimension 1 faces are parallel to each other, and the remaining ones are the ones which are tilted at 45 degrees angle or something. So this is the realization that you find from this blossom quiver algorithm, and one can show that if you start with a quiver like this, which is so this quiver, dissection quiver, which is not cyclic, then this is precisely what U. Thomas and Mate, etc. got from quiver representation theory. But now this algorithm is so rich that we could apply to our second example. So I'll just quickly do that, which is not an associahedron. So the second example we have was like a bit trivial example where we the dissection was a bit irregular. So again, I only draw hollow vertices on the external edges which are incident to the chord that I'm starting with. So that's why this one I leave out, and then I have so now you see that there is only one equation because there is only one. It's just 1 point. Quiver is just 1 point, and that equation is easy to write down. It's x1 tilde 3 tilde plus x2 tilde 5 tilde is a positive constant. And so that so even though the full space of possible chords is again 5-dimensional, this realization sits only in a plane which is and it just sits like this. So this is the x2 tilde 5 tilde equal to 0, and this is okay. So this is the same algorithm you just follow, and you can obtain for any accordiahedron, that is the combinatorial polytope is found from starting from a reference dissection, we can convexly realize it. So and the rules are really this simple, like there's nothing more in these rules. So I will just now state the main result, which again is something that most of you here will be more expert in. But the reason that if you wonder where all these rules came from, so I'll just because of lack of time, if I have final few minutes, I will just maybe say a little bit about this. That starting with, so this is the main theorem which connects this way of realizing with the older ways of realizing the using quiver representation theory, starting with the blossom quiver. Again, this may not be the most accurate way to state the theorem, but this is a sort of a poor man's way to understand it. Q star flower, for example, there is a fan, let me just call it Fn of G vectors, which I am just going to indicate as G. So for this example, there are 3 G vectors, 1, 3, 1, 3, 1, 4, and 1, 3, 2, 1, 4. And one can show that this forms a fan, a complete fan, and then all the polytopal realizations where this becomes a normal fan are precisely these ones. So all the this one that we have, sorry, I should not have erased it, the one that I drew. Sorry, this is, of course, this will have all the, apologize, this will have all the, you can, of course, you can write G vectors for all the 5 dissections. So this is just for the experts. That so these are the realizations where that the normal fan that you obtain from here, these are the G vectors that you obtain just from following this quiver. So they associated with this blossom quiver, we can write down some G vectors using some simple combinatorial rule. And you ask, what are all the possible polytopal realizations where this fan is the normal fan? And these are all of them. Like there is nothing more. So they exhaust all such polytopic realization. So that's why it's not surprising that all the ones that quiver representation theory gave us also are included in this way of doing things. So is there any question at this stage? Yeah, so G vectors are some, I didn't write down, maybe I can just, maybe I can quickly write down the G vector in 1 minute for this example. Yeah, so just. G vectors, I mean, one cheap way to write the G vectors is the following. So let me draw this again, sorry. Let's just start with this reference. And like again, let me draw all the hollow vertices for the dual pentagon. And suppose I want to write a G vector for 1 tilde, 3 tilde. Okay, this part. Then what I do is I look at the, so you see that it's only intersecting 1, 3, and it is intersecting it in like an inverse Z. So the rule is that if it intersects, so our basis for the G vector is going to be the reference you start with. So the basis for the G vector is 1, 3, 1, 4. And the rule is that if 1 tilde, 3 tilde is intersecting 1, 3 in inverse Z, you put 1 here. If it's not intersecting 1, 4, you put 0 here. But if you look at slightly more non-trivial example, let's look at 2 tilde, 5 tilde. Then you see that it is intersecting 1, 3 in a Z and intersecting 1, 4 in a, so it's intersecting 1, 3 in a Z and intersecting 1, 4 in a W, head of inverse W. So whenever it intersects something in a W, this is 1, 4, then it's 0. When it intersects in Z, it's -1. So this is -1, 0.
So for Z, it's 1 and minus.
For inverse Z, it's 1. For Z, it's -1. And for this, it's 0. And if it doesn't intersect, obviously it's 0. So you can write G vectors in this basis, where the basis is given by the reference dissection. Now you ask, okay, what are the polytopic realizations where this is the normal fan?
Okay.
And all of them are these ones. This is what they prove. And of course, as you can see that you could do this not just for triangulation, but even for the Stokes polytope, like the quadrangulation. You just write G vectors following the same set of rules. So you got the, so you have this normal fan coming from combinatorial data, and you have convex realizations which are compatible with this normal fan, for which this is a normal fan. So you have a fan and you have a realization for which that's a normal fan. Okay, so that's where the math part ends now. So we have all, now we see what this has to do with physics. So I'm just going to say one thing, that we realize that this equation look a little complicated, but in the end, we could show that this equation can be packaged in a very, very simple way, which can be directly used. So I'm going to state the final result, which is actually quite simple. So start with any n-gon. And start with any dissection, a reference dissection. So I'm just drawing some. So this is some D. So it can have quadrilateral, triangle, whichever. Now, so given a D, now you look at, so given a D, now you look at a DC, which is obtained by from D by one counterclockwise flip. That is just to give an example of what I mean. If I start with a D, which is 1, 3. So if D is 1, 3, then DC is simply 2, 5. Just do one flip, see where you hit, that's part of DC. So you do it for all of them and you will get a set of, so if you initially had K chords, then this will also have K chords. And that's what I call DC. And now all these equations for any D can be packaged in the following way. So write the equation as follows. Look at, I'm going to define something. Let me define Yij as a variable, which is Xij plus Xi plus 1 J plus 1. Actually, I should strictly put tilde here, consistent with our notation, minus Xi J plus 1. Oh, sorry, small x, I apologize. These are the same axes we used to write the equation. This is the same axis. I'm just defining some y, which is a linear combination of x. You will see why. It just helps us repackage this equation in a remarkably simple form. Now, all the set of equations can be written as follows. So this is Yij equal to Cij. Write this equation for all ij not in DC. So this is this equation for any D. So it's just a final summary of the convex realization, which can be packaged really in this very, very simple way. That you just define this, and as we will see, these y's have direct relation with physics variables, which is where the connection also comes. But I hope this is clear that the same equation we could write in this form, where the reference information has gone here, because DC came from the reference D that I'm starting with. So for each reference dissection D, I get a convex realization given by the set of equations. And of course, yeah. So I hope that's okay. So now I'll give you the connection with physics. And so now we have the following information from math, that I have some space of xi(x). So I'm just going to call it xij. It is just some Cartesian space of dimension r to the power mod of the number of dissections. Like that's all. And then I have some polytope sitting here. So let's just do some. Just drawing it arbitrarily. And then now the statement is the following, that if I think of this not as a Cartesian space, but as a projective space, then, so if I just think of this RD as, it's just projective, I say, so PRD. Then in this projective space, there is a unique form of same dimension of, sorry, this, I apologize. This D is, I shouldn't call it D. This is, this embedding space is space of all possible chords, which is always very large, right? It's the n into, if it's an n gone, it's n into n minus 3/2. That's the, like the big space. That's all possible chords you can draw. So that's the space in which I'm realizing all my polytopes. And now the statement is that, but of course, as we know that the polytope actually sits in a smaller space, which is just spanned by the reference number of reference dissection. But now the statement is that if you just projectivize this space, then there is a unique form of dimension polytope, same dimension as the dimension of the polytope, which has simple poles on all faces of the polytope. And only on the, maybe I should write here, and only on the face.
So your D here is now the big D?
P, I'm just, yeah.
Capital D. Capital D is the n into n minus.
Yeah, sorry, this I should. Yeah, what I had in mind was that in the end it gets sit inside the smaller space. So that's why in the end that's all we need actually. We only need the space coming from the number of dissections, reference dissection you start with.
Right.
So actually it's okay. I mean,
differential form lives, this form lives on which space?
Okay, yeah, actually this will live on the, so this form lives on this space. So let me give you an example. So, I mean, I could start with the form in the big space, but it wouldn't matter. So just to give you an example, in the previous case, we have a x13 and x14 in which we realize the polytope. And now the statement is that, like, think of this as a two-dimensional projective space. And in that I'm writing a form. And that form is such that it has singularities on and only on all the faces, not just two-dimensional one faces, all the faces of this polytope. And there's a unique form like that. And that, I think the uniqueness comes only if you projectivize this space. Otherwise, you will not get a unique. So, so now let me write the form. And that's basically the S matrix. So even now at this stage, there's no physics input. It's still math. And in the last minute, I will put some physics input. So these are typically called, so let me write these forms just as an abstract thing. So the form is the following, that it's, so maybe for this example, I will write, maybe it's easier. So it's a 2 form. So I'll just write it as omega 2. and it has a following form. So it's just given by d log x13 which d log x14 minus, I will explain where the sign come from, d log x13 which d log x35. So there are 5 terms corresponding to 5 vertices of the 5 vertices of the triangle. So minus d log x24 which d log x14 minus d log just for completeness I will write the whole thing, d log x25, and I think I missed one more. Sorry, this should be plus and then minus d log x35 which d log x25. And one easy way to understand where the signs are coming from is that you can show that because you're in projective space, it shouldn't matter if you scale all the x variable with the same function. So if I scale all the xij's with some function of xij, then this form should remain invariant. And you can actually check that the signs ensure that this form remain invariant. And you can ask where this, how did I fix the sign? Up to an overall sign, it is easy to see how we fix it. That every time you do one flip of a dissection, so you want from 1, 4 to 3, 5, then you change the sign by 1. Here also similarly, you did 1, 3 to 2, 4, but you keep 1, 4 fixed, then you change the sign by 1. But you do one more flip, then you change sign again, so you get a plus here like that. So this is the form, that's a unique form in this projectivized space. And now the statement is that if you now pull back this form on this realization that mathematicians found for us, then that realization looks very nice. So in this simple case, if you just restrict it to the, so let me call it ABHY, 2-dimensional. So if you just pull it back on ABHY 2-dimensional, then it turns out to be this. I'm just writing the final answer. So the basis, the way I've chosen the basis is the reference dissection. Okay. Now, of course, if you change the reference, this will change. But what is remarkable is that what multiplies this will not change in the case of the associahedron. And it turns out to be all possible terms that just put all of them, 5 of them. Okay, so I hope, is there any question here? How much? All these are. So at each pairing, there's a compatible chord. So each pairing is given by triangulation of the, but I could do this even for the accordiahedron. Like I just wrote it for triangulation, but now notice I could do same thing for accordiahedron. So maybe in the remaining 2 minutes, I will tell you where physics came. So till this point, there is no physics. And now I will tell you where the physics comes in. If you now identify, so let's go back to this x variable. So what are these x variables capturing? So x13 is this chord. And you could have asked in the beginning why physicists should be interested in looking at dissections. And then the answer really comes from our obsession with Feynman diagrams in physics. That if you look at this dissection, then you immediately notice something, that if you draw this, if you draw the graphs which are dual to this, then this triangulation, so for example, I take this one, then this triangulation is dual to the following graph. And this graph is what is called Feynman diagram in quantum field theory, where 2 particles can come collide and produce a 3rd particle. So that is why we start looking at dissection in the first place, because they are naturally related combinatorially to Feynman diagrams. And now it turns out that then you can ask, okay, in that context, what is the meaning of x13? And one meaning of x13 you could give in this case is that you have 2 particles coming in. So sorry, now I'm using some physics language with momentum p1, and you have another particle coming with momentum p2. And what is being added here is total momentum p1 plus p2. But p1 plus p2 is a Lorentz vector. It's not an invariant. What is invariant in physics is the square of this, because everything should be Lorentz invariant. And so you see that this quantity is what is naturally tied to x13. Morally, if you similarly look at this x14, then you can immediately check that it is sort of related, spiritually tied to p1 plus p2 plus p3 squared. So now if I make this identification here, I get the S matrix of a theory, quantum field theory, where you allow two particles to collide and come out. If you did the same thing for the other, sorry, I will just take one more minute. If I did the same thing, but for the accordiahedra, so if I do the same thing for this, I have this accordiahedra that we drew, which was x13, x25. This was the accordiahedra we realized, and that came from a combinatorial polytope, which came from just one chord like this, and this chord is dual to this graph. So where you are allowing two particles to come, collide, travel, and splinter into three particles. So this is a different graph than this graph that where you are always allowing at each vertex it only splinter in two. So you can believe me that that's a different theory, quantum field theory, than this one. And now you ask, okay, if I did the same form pullback thingy here, the form I would have got is 1 by x13 plus 1 by x25 dx13. And now again, if I identify x13 with this physics variables, then you can check that this is the S matrix for this process, that two particles came and then collide and splinter into the. Yeah, I ran out of time. Whether I could have told you that this procedure. Now here, the one extra input we have put is literally, there is just like a moral connection. I made a literal connection when I did the substitutions in physics. But you can ask how robust they are. Like, what if I change this to, say, some coefficient plus some beta? What if I change this to some other coefficient plus some beta prime? Then will this form still give me S matrix of some theory? And it turns out it will give me S matrix of a theory where your particles have different masses and the probability of them colliding and splintering is different than in the previous case. So really this carries information not about like one quantum field theory, but an infinity of quantum field theories. So that's the, and okay, just I did it for unpunctured polygon, but these things really powerfully generalized to, if you start with dissection quiver associated to like a hole in the center. And in fact, here we find like new class of polytopes which don't come from cluster algebra or don't even come from what are called gentle algebras. So maybe I just stop here.
AV team, can you please enable the online participants to unmute themselves? Questions, comments?
Hello.
Hi.
Yeah, so if you integrate this form that you've got, that is that's what you're calling the amplitude, I suppose.
No. This no integration.
No integration.
No. Just this itself. We just identify this with the. If I identify this with this,
yes,
then it's a S matrix of a theory where you are allowing two particles to collide and splinter. No integrate. Like this is the answer.
Okay.
So, but you are right that if I had this punctured thing and I follow this procedure, what I would get is something which is called a one loop integrand in quantum field theory. That I have to integrate, but not at this level where you don't have any puncture. This is the S matrix.
And the one loop integrations, will they be finite? I mean, one loop or two loop?
No, so then we are in the physics domain where all the issue we face in integrating these things will come.
Yeah.
And in this case, it is not clear that the integrated answer has any geometric meaning of this type. What is clear in the one loop case is that what goes inside that integral is also a form associated to some convex realization of some polytopes coming from some dissection quivers. But it's what fits inside the integral in the one loop case.
Okay. Yeah. Thank you.
Other questions or comments?
So I have a question. What is about this particular ABHY associahedron that makes it uniquely suitable for physics?
Yeah, that is, I think, I would say now a really striking surprise in my opinion that, okay, so the way ABHY discovered is through some physics argument. Like they wanted an answer, which is this S matrix, and they asked, what are a realization which would give me this answer as opposed to say, this times phi times this, which is not an S matrix. So that is dictated by the slopes of these faces. So that's how they discovered it. But that was like going backwards, going from physics in some sense. But now what we realize is that what we get intrinsically from math is exactly that. Like we get without any physics input. We really didn't use any physics input up to here. So it has no business of making connection with physics in some sense, but it does.
Associahedron, the
Yeah.
associahedron given by Loday.
Yeah.
And if you look at Loday, well, if you look at the S matrix, do you know the explicit form of that S matrix?
No. So there we will, the form we will get, it's a very good question, an interesting question. That so, like for example, if I take, I think his realization is where no faces are parallel. So, like for example, for the pentagon, you will get something. Like something like this, some obscure thing like this, like even sitting inside, say, the x1 3 tilde x1 4 tilde space. Now you can ask that if I do this form pullback thingy, what I get, is it an S matrix of some quantum field theory? This is not known. So that's the thing that, in general, the realizations we get, do they have anything to do with physics? We don't know. But what is remarkable is that Loday realization didn't come from only the combinatorics of quiver. He had to put extra input to get this realization. So the realizations which come without using any other data seems to give physics connection directly. Although I don't have time, I can tell you privately that we see that this has some relation with physics, but it's very much in the initial stage. We don't know the full extent to which this is related to. But that's the point. Of course, you could draw the realization pentagon in so many ways. But the one that math gives you most naturally, I would say, is the one that is directly making connection to physics.
Right. I just had a small question. The Cij constants that you wrote down,
where
does that come in here? That does not appear in the form, is it?
Yeah, that will not appear in the form in the sense that, of course, you see that here we solved we have 5 variables and we solved them in 3 equations. So the 2 independent variables are x13 and x14. So if you write x25 in terms of these variables, the C's will appear.
But when you pull it back to this,
So if I substitute this in terms of x13, x14,
then you will see those
variables will appear.
So what is the physical interpretation of those Cijs then?
Yeah, that's a very good point. So that information about Cij actually is the following. That's how ABHY discovered this, actually, the physics argument that so you see that when we draw these dual graphs, so let me just give one example. So suppose let's just start with a foregone, simplest case, and triangulate it. So there are 2 possibilities. And so we have 2 graphs which are dual to it. But as you know, both are planar graphs. But as you know that in general, if you took any quantum field theory where what is allowed, there is a channel which is not planar, which is the U channel. And the fact that in planar graphs U channel doesn't occur means that you have frozen U. And it turns out that so in this case, this C constant, there will be only one constant, and that is exactly equal to minus U. So that means you have frozen to be minus the negative constant because C is positive. That means U is forbidden by physics arguments, right? It's negative. So that's the. No, but so it's massless if you make the direct identification of X with small x. Now, if you ask what if I identify X with alpha, then you start getting massive theories also. So in that case, you will be positive, but you will always be in the forbidden region in that case also. You can check that. Yeah.
I think there were questions online. Shrikant, did you have a question?
Yeah, I have a question. Basically, when you say that, many of these things, when we compute, we get S matrix of some theory. Does it mean like you construct a Lagrangian and you work it out using that and it matches?
Yeah, exactly. That's exactly what I mean. So, so I didn't have time to say that the Lagrangian which gives this as a S matrix is what is called a biadjoint phi cube scalar field theory. So it's a scalar field theory where scalar have some flavor indices, some extra Lie algebra indices, which ensure that only planar graphs occur in the S matrix computation. So I agree with you that when I say that, I mean that there's a local Lagrangian which will produce this STS matrix.
Okay, so but you can also get the theories which does not have a Lagrangian description. Is that true?
Yeah. But we are very much far from. I mean, if you ask me what is can I get Young-Mills S matrix through this? I don't even know the answer to that.
Okay.
So far, all we are getting, although we are getting a large class of S matrices, they are all pertaining to scalars in this case. I must say that all this program I'm describing is coming from a much older program called amplitude-hedron program, where everything was done for what I call supersymmetric quantum field theories, but where these polytopes don't live in this simple Cartesian spaces, but what are called twistor spaces, etc. Where you are getting all this is done, but for supersymmetric theories. But we are right now in the domain, since you are asking, I'm just using some physics word, in what we call non-supersymmetric quantum field theories. And in that case, we only know how to get scalar S matrices so far from this program. We do not know how to get, like, say, QED or Young-Mills S matrix. Yeah.
Okay, thanks.
Yeah, there's a question.
But the Manjunath also. Yeah.
Sorry.
Yeah, so this this particular construction is for single particle theories, right?
No, that's the thing, that now once you make identification of this small x with the physics, then you can get S matrix for different particles colliding with different masses and propagating. Like, you have a rich class of theories that I didn't have time to go into. So this is a math result, and this can give you a zoo of quantum field theory with different masses, but they're all scalar particles. Like, they don't have.
Okay.
Yeah.
So my next question is that is there is there research going on where so this sort of construction is considered actually fundamental, and rather than the Lagrangian?
Yeah, I mean, exactly. That's the point. That somehow the point is that there's a long history of S matrix in quantum field theory, where we know that Lagrangian formulation is highly inadequate, and we are looking for principles which are more fundamental than starting from Lagrangian and Feynman diagrams, because we know in many cases where, one example is what someone asked earlier, this Young-Mills theory, where there are specific, so you take these what are called glue ones, you collide them, and there are specific S matrices, which if you do Feynman diagram, you will take thousands and thousands of maybe pages, you write, but there are other methods where you get, like, in few lines the answer. So you know that there must be something more fundamental than Lagrangian. Yeah. So that's the goal of all these programs, that, to find a, like, S matrix is just a function of momenta. So what are the functions which are S matrices of quantum field theory? That's really the question. It's like a classification question at the end of the day.
So this is, this is one program which is.
So this is one program which this is a far dream, but you see that this is telling you that, okay, all the functions which come from forms of polytopes, which are convex realization of dissection, combinatorial polytope comes from dissection quiver, they are always S matrices. That's what we seem to be seeing. So there is we are moving in that direction.
Okay.
But yeah, it's very early to say that way.
Thank you.
So the normal polytopes of these realizations, can you determine them? The normal fans, sorry.
Yeah, so you mean the G vector fans? Is that
the normal fan?
So I thought that my understanding of this is that you look at the G vectors coming from the dissection quiver, the combinatorial rule we wrote down. Now you ask, what are the polytopal realization for which the G vector fan is the normal fan? And all of them are only these.
Yeah.
That's the theorem.
Okay.
That if you start with any dissection quiver or this blossom quiver, and what are all possible polytopal realization of the normal fan of the G vectors, of the fan of the G vectors.
Right.
And all polytopal realizations are the ones that came from these deep pick rules.
Okay. And that path algebra that you mentioned, that's a cluster algebra, or?
If you, this is something that I don't know very well. I think that, of course, for the triangulation, so you see that if you start with triangulation, then it is a type A cluster algebra. But if you start with other dissections, like the one that we initially discussed, then it's not a cluster. Like, for example,
Yes, with the quadrilateral.
Exactly. The
quadrilateral.
Yeah, then there's no cluster algebra here.
Okay.
But this is what is called the gentle algebra. I think, if you start with this path algebra of quiver and quotient by the ideal of two-sided paths where all lie inside the cell, and that is the algebra, but it's not a cluster algebra, I think.
Okay. Thank you.
So in this 2-to-2 scattering, it seems like this crossing symmetry is manifestly built in, right?
Yeah, in this case, yeah.
Yeah.
But it's a tree level. It's not very non-trivial example for crossing.
So in general, you can do this M2N scattering as well using.
Yeah. I mean, this is for any n particle scattering. What is, I think this, so far we don't have much to say about crossing, but sorry, I didn't because of lack of time. What is amazing is that, at least I find what is amazing is that the unitarity is, you can ask why we got S matrix, where is the information about what we call unitarity? And that information is the combinatorics of this polytope. So if you look at Associahedron, this is a remarkable property that so you start with some n-dimensional Associahedron, combinatorial Associahedron, then any, so you take, like, for example, take like 4-dimension 1 face of this. Okay, so you get some polytope. Let me just call it Pn minus 1. Now, what is amazing is that this Pn minus 1, it is either An minus 1 or product of 2 lower dimensional Associahedra whose dimension add up to n minus 1. What I mean by this is the following, that if I look at 1-dimensional Associahedra, it's just a segment. 2-dimensional Associahedra is a pentagon. So if I look at a 3-dimensional Associahedra and I look at all its faces, then they are either squares, which are product of this, or pentagon. You never have a face which is a hexagon. And this, you should immediately recognize that this is the origin of unitarity, right? That when you go on shell, you always get product of lower point amplitudes on shell, and that properties keep captured here. And that's true for all accordiahedra also. So so unitarity emerges from here, and locality emerges from the property of the form that there's a unique form which is meromorphic, which has only simple poles. So both of these emerge from the math side, like they are consequence of what mathematics gives us.
I see. So in M2N scattering, you take this Xij's to be this general Mandelstam invariance kind of thing. Like,
yeah.
And then once you substitute that, you get this.
Yeah, if you just directly identify them with Mandelstam for massless particle, as Naveen was saying, you will get massless, but there is a lot of this will also capture for you massive phi cube or 2 different scalar with different masses coming, right? If you identify them correctly within the physics side.
Yeah, so I think there are many interesting questions and a lot for discussion, but in the interest of time, let's move over and have the discussion over coffee, and we'll meet again at 11:30 for the next talk. And let's thank Alok again for a very nice talk.
Thank you.